Okay, welcome to everybody for the November session of the Young Seminar of the Italian Society of Statistical Physics. And this afternoon, as usual, we will have two speakers, Jerome Garnier of Bocconi University and Lindsay of Teli, who is working at the Nanoscience Institute of CNR in Pisa. The first speaker will be Jerome Garnier, and just a very, very short bio. Jerome in 2020 got a master in physics of complex systems in Paris, and in 2023 he got a PhD with Jean-Philippe Bouchot and Michel Benzaken at the École Polytechnique with a thesis Navigating Radical Complexity, the Influence of Disorder, Non-Relaxational Dynamics, and Learning on Aggregate Coordination. Presently, he is a postdoc researcher at Bocconi University with Marc Mézard, and the title of his talk, you can read it, Unlearnable Games and Satisficing Decision, a Simple Model for a Complex World. So please, Jerome, 25 minutes. Thank you.
All right, thank you very much for the introduction, and thank you very much for having me. So today I'll talk about a topic that I did when I was a PhD student. So as you said, with Michael Benzaken and Jean-Philippe Bouchot within the chair of Econophysics and Complex Systems at École Polytechnique. So to start right in, I mean, of course, this is a lab that works on the physics of complex systems, but maybe just I should introduce what exactly we mean by this. So in my perception, the physics of complex systems really kind of starts with the theory of spin glasses, which I'm sure many of you have heard about, and that in a nutshell propose simplified models to describe disordered magnetic states. And so to make a long story short, a very important ingredient to understand the peculiar behavior of some of these disordered magnetic states that you can find in some alloys is actually to introduce random bonds between the interacting particles. And in particular, these random bonds are important because they lead to something called frustration. So frustration is typically illustrated with this little drawing. So you can imagine you have three particles, A, B, C. So they can have a spin up or down. And then if you introduce random bonds, well, what can happen is that two of them will want to align, another two will want to align, but the last two will want to oppose. Okay, so clearly you can see that in this situation, not everyone can be happy. And so this is what is often referred to as frustration. And frustration is pretty important because in what you can consider as seemingly simple optimization problems, so at least easy to state optimization problems, here it would be the Hamiltonian of a spin glass that you want to minimize. Well, these can become very complicated due to that frustration. And so, of course, Italy had a very big part in understanding, what happens through notably all the work of Giorgio Parisi, who was awarded the 2021 Nobel Prize, and all the co-workers associated to that. But what's really interesting is that actually this notion of frustration, in addition to being, theoretically challenging, also has many applications outside of these disordered magnetic states. And so, I mean, it's quite in topic these days because, of course, this year the Nobel Prize was awarded to John Hopfield, which I understand some people weren't necessarily too excited about. But in any case, it's really some form of application of these ideas from spin glasses in a completely different context, which is neural networks. And amusingly, at least to me, if you actually open the seminal work of Mézard, Parisi, and Virasoro on spin glass theory, what you find in the very first lines is that the example that they use to describe frustration is that of wanting to be friends with both a Mr. White and a Mr. Smith, who unfortunately hate each other. And then it's rather difficult to be a good friends to both of them. And this is a prototypical frustrating situation. So, okay, from that standpoint, it seems pretty natural, in fact, to consider that socioeconomic systems, through this lens of physics of complex systems, deserve a closer look through this lens of frustration and heterogeneous interactions. So, however, it turns out that understanding these frustrated systems, it took a long time, and it took also some, let's say, non-exact mathematics for a while, numerical simulations, etc., which contrasts a lot with the traditional theoretical economics. Indeed, in the mind of some of the founders of neoclassical economics, such as Léon Walras, economics is a mathematical science, and they believe to the same title as mechanics, and in this context, it's not statistical mechanics, it's really analytical mechanics. And so building upon these ideas from the beginning of the 20th century, theoretical economics actually evolved a lot in a very axiomatic fashion. So trying to build, let's say, provable, mathematically tractable models, but assuming in particular the idea of representative agents. So instead of considering millions of interacting individuals in an economy, taking one representative household, maybe one representative company, and then one representative central bank, which in this case sort of makes sense, and describing the system only in this very reduced way. So completely throwing away, in a sense, the heterogeneity and keeping the number of, let's say, constituents to a very small number. Another idea that has been really preponderant is that the economy is in an equilibrium. So equilibrium in the sense of economics is not really the same as in the sense of statistical mechanics, but really in a nutshell, it means that any sort of dynamical behavior only emerges through an external perturbation. So in a sense, if something happens in an economy, is due to something exterior, and then it will go back to an equilibrium, or maybe in some cases go to another. But really, the economy itself doesn't have, let's say, endogenous dynamics that sort of live on. Finally, a very common idea is that also of rationality. So this, I'm sure you've heard about, meaning that economic agents such as you and me, we make our decisions as perfect optimizers. And an extension of this is also the idea of rational expectations, which is, what not only are we rational, but we perfectly use all the information at our disposal in order to sort of build very faithful predictions for the future and then react accordingly to these rational expectations. For instance, one of the big proponents of this rational expectations is someone called Robert Lucas, who was in fact awarded a Nobel Prize in economics this time. And, just to show basically following all this work on these axioms, in 2003, Robert Lucas declared that the central problem of depression prevention had been solved, and had in fact been solved for many decades. So using the models, really, there was no problem. Unfortunately, we all know that following the 2008 financial crisis, there was, pretty significant economic depression. And in fact, even further, this crisis is a good example of some of the things that were wrong, because really here, finding the exogenous source of the crisis is not easy, and there's no COVID involved, there's no war involved, and really it seems like the economy within itself sort of went all the way towards a crisis. So, okay, this is a pretty grim, let's say, landscape. However, to be honest, and not too controversial either, there are also many people working beyond these traditional assumptions. And so to name a few, there's been the emergence of many theories of what's called bounded rationality. So we're not purely rational. There's sort of some, variations around this. One approach is notably to go towards probabilistic decision making. So in a sense, you're kind of not deciding where the problem is from, but you say, okay, maybe in probability, we're good optimizers, but then you allow for fluctuations. And this can be motivated, by either the computational cost to actually do the exact optimization, or even some information, cost that you can interpret and then, build these probabilistic rules. And so there's been work in the 50s by economists, and actually in the 90s also by physicists around these ideas. An alternative that is quite interesting, that I'll come back to, is more behavioral. It was developed by Herbert Simon, an economist. And so is the idea that we pick so-called satisficing decisions. And satisficing is basically a contraction of satisfactory and sufficing. And really here what we're saying is that, I don't know, if you want to buy a car, you might not look for the best car in the world, but really if you can afford it and it works fine, you're happy with it, then, the problem is over. So really this idea is to say, why perfectly optimize when really probably above a certain threshold of satisfaction, things are good enough. On the other hand, I also mentioned, the lack of work on heterogeneity, and I think this is changing actually. In 2019, Estelle Duflo was awarded Nobel Prize in Economics for notably, working on how poverty and, the certain economic levels affect, in fact, the very decision-making process. And so given the large amount of inequalities in capital and revenues, it makes sense that, maybe putting all the households together in a single representative household is not really going to cut it if everyone with different revenues reasons in a slightly different way. So there are definitely some works ongoing to go beyond these assumptions. However, when you go beyond these assumptions, the problem is that, there is the emergence of what's now called complexity economics. And what happens is that usually we go to the other extreme, which is very large scale, data-driven, so informed, so use data from the government, etc., in order to calibrate large agent-based models that will have tens, dozens of parameters for potentially each of the economic actors that can be millions that you simulate in a computer. And as physicists, we also know that doing this, it's very valuable, but at the same time, you may lose track of what which ingredient is doing and what are the necessary ingredients to get some sort of qualitative fact. So sort of midway, and where I think obviously physicists, and particularly statistical physicists, might have a role to play, is towards what I'd call phenomenological or toy models that really are going to allow us to sort of more track the mechanistic role of different ingredients by going into very simplified settings. So just to illustrate this in the socioeconomic context, there's a model that I think is quite striking. So imagine you have a big grid, two-dimensional, that represents a city. And on this city, each site can be occupied or empty. So it's really a lattice gas model if you want. And so here I sketched one where the dark sites are occupied and the light ones are empty. And you further subdivide it into neighborhoods that are the black squares. And then you sort of assume, well, each agent wants to be in a neighborhood that's sort of half filled. So because, they want to have some stores, but at the same time, they don't want to be crammed into small apartments. So if you imagine something called the utility function, which quantifies the satisfaction of agents, it could be the plot here on the left. And so if it's half full, you add the maximum rho star is equal to 1/2. And then I decide to simulate this system. So take individual agents and ask them if they want to move, and to make the decision only based on their own satisfaction. And so there, if you go through the representative agent type of reasoning, you would think you start from a homogeneous distribution, you'll stay there. And in fact, it's not at all what happens. And if you let the system evolve, you get into concentrated suboptimal distributions of the density. And in fact, what you need to explain this is specifically statistical mechanics. So of course, I'm not claiming this model really represents any geographic organization. However, it allows you here to pinpoint the fact that individual maximization and global maximization are really not the same thing, which is not something that is so commonly accepted in economic theory as it stands. So long story short, this is sort of the level of fidelity that we want to place ourselves in. So now the objectives that we had in mind when we started this project was essentially to introduce a really minimal toy model to understand the roles of specifically, well, heterogeneity. So because I mentioned that it's been not that studied actually. So here taking strong inspiration from disordered systems and spin glasses, and then add a couple ingredients that are non-reciprocal interactions, because of course, I'd say magnetic particles, they interact in obviously a symmetric way. However, if I want to imitate someone, nothing guarantees that they will want to imitate me back. And finally, there's something that's also quite important, which is the possible effect of individual learning from the agents on the dynamics of the system. Because if you talk to some economists and you say, well, listen, this rational expectations paradigm, I'm not sure, because the world is too complex, they'll say, okay, yeah, that might be right. However, we believe that rational expectations can emerge in the long run, so given enough time, provided the environment kind of remains stationary. So okay, it's a bit of a vague statement, but there is this idea that regardless of how complex the world is, through kind of iteration, you will sort of find, the rational expectations that you assume from the start. So what I like about it, let's say from a physics point of view, is also that then, these two ingredients, non-reciprocal interactions and learning, they're not so common in physics. So, why not? And see what sort of new physics might emerge from this. All right, so let's talk about the model. So as I said, it's strongly spin glass inspired. So, and it aims at being as simple as possible. So maybe disappointingly, it goes to binary decisions. So here we assume that every agent labeled I, so it could be someone like you and me, plays plus or minus 1 at a given time step t. Okay, and so then you can interpret this if you wish, like it could be being left wing or right wing, it could be Brexit, no Brexit, or it could be buy or sell a stock, whatever you want. And then you consider n being large agents as such that interact. And importantly, for the learning part, you assume that their decision at a given time step to pay plus or minus 1 will depend on the gains they've just realized, so what the outcome of the game at the past time step, but also older iterations. So they have some memory of what happened in the past. So let me illustrate this a bit more clearly, perhaps. So every agent picks plus or minus 1 based on some preference that you can, for example, randomly initialize. And then since they all play together, what you look at is whether I have the same decision as the people I want to imitate, and I have the opposite decision to those I want to oppose. So really, you get some reward that depends on your match or mismatch with others in the system. And so then what you'll do is you'll use this sort of reward that you just got and the ones that you have in the past if you're at large time steps in order to update your preference that will then dictate how you play at the next round of the game. And so you iterate this. To be a bit more precise, so here bear with me because it's a bit, let's say, less nice than a sketch. But so where do we put the different ingredients? Well, the disorder, the heterogeneity comes in through this reward specifically. So I said you wanted to match or mismatch others. So here, for example, you have this matrix J, interaction matrix, essentially, which if Jij is positive means agent I wants to imitate agent J. And if it's negative, you want to make the opposite decision to them. And this really is where conveniently you fit in the link with spin glasses, because you take these interactions to be random, Gaussian distributed, but really could be anything. And this is exactly like the spin glass model of Sherrington-Kirkpatrick. And importantly, here we assume the network is fully connected. So you interact with everyone. But so this is where you put some disorder, and then you can also fit the non-reciprocity in this interaction matrix by introducing a parameter epsilon that really interpolates between a symmetric random matrix and an anti-symmetric one. So just let's not look at the equation too much, but if epsilon is equal to 0, this parameter, then you're fully reciprocal. You have symmetric interactions. If it's equal to 1, then you kind of randomly draw the opposing entries. So there's a 50-50 chance they'll have the same sign. And if it's equal to 2, then you have something that's known in socioeconomics that you might have heard about as a zero-sum game, meaning that if I win, then the person I'm interacting with necessarily loses. So the matrix is completely anti-symmetric. And then you can, of course, vary this parameter epsilon continuously to get anything in between. All right, now the learning, as I said, you accumulate sort of these rewards in time. So what we use is sort of the simplest thing, I guess, that you can think of that's a form of reinforcement, where here you have this variable Q that's really the incentive to play plus or minus. And so again, just to give you the main features, you have this parameter alpha that's a memory loss rate, such that the only thing to remember is that if alpha is equal to 1, you're memoryless. So you play just based on the last outcome of the game. And if alpha goes to 0, then essentially you remember over a time scale that's 1 over alpha. And when I say you remember, it's essentially that the reward that you consider for the incentive, rather, that you consider to make your next decision is an exponentially weighted moving average of the past rewards over this period, 1 over alpha. Then finally, and I don't want to expand too much on this, but I'll still mention it, we do put bounded rationality because I made a point of mentioning it before. So here we follow kind of the simplest approach, which is to choose in probability. So that is to say, you have this parameter beta that's known as the intensity of choice, or let's say the rationality parameter. And that means that when beta goes to infinity, you select the choice that has the highest incentive accumulated in time. So you're a perfect optimizer. And when beta is finite, then you do so with probability. So you would need to describe the system using, let's say, averages of decisions or expected decisions that we call intentions. And conveniently here, you might recognize that it plays exactly the same role as the inverse temperature. I won't expand too much on this. It might seem like cheating, but actually it's socioeconomically motivated as well. So then, you do what you want with that assumption. However, so in most results I'll show today, I won't mention this too much, just in the interest of clarity and time. All right, so here are all the different ingredients. Just to summarize again, so you have disorder through the interactions. The non-reciprocity parameter is epsilon, and the learning parameter is alpha, which when alpha is equal to 1 is memoryless, and when it decreases implies long-term memory. Okay, so now you have the model. You could run it. You could work on it theoretically, but let's maybe start by thinking about what an economist would think about, which is the equilibrium, i.e. here the fixed point. So again, I'll take beta going to infinity, so perfectly rational agents and their binary choice. And then what you have for the fixed point equation is something that I'm sure some of you have recognized as the zero temperature Tallis, Anderson, and Palmer equation that describes the SK model I mentioned before, if the interactions are reciprocal. And actually, I just wanted to mention this. I think it's a nice paper where they introduce it. Of course, it fueled a lot of research after. But so what they say is that they reduce the problem to finding solutions to the mean field equation here, but on their own admission, it's not much easier than the original problem. Why is it so? It's because J is still a large random matrix. So really finding configurations that satisfy everyone is not so easy. And the really important thing that I want you to keep in mind is that let's say the outcome of this is that there is an exponential number on average, but actually pretty much all the time in the parameters that we consider here, of solutions to these fixed point equations, and they turn out to be also, for many of them, quasi-equivalent. And so this will really be an important feature, and I want you to trust me on this. Unfortunately, I don't have time to expand on it, but that remains true actually also when you're not strictly reciprocal, but you still maintain a high level reciprocity, and when the rationality in our system is finite, so you have some fluctuations in the decision making. But okay, you have an exponential number of fixed points. However, now I tell you, okay, we run the dynamics or we study it, and I draw a dynamical phase diagram based on the non-reciprocity epsilon and the memory loss rate alpha. And if you don't put learning, what you first observe is that you look at the two-time correlation of the configuration of the system, and it actually oscillates. So if you don't have memory, agents overreact, and you sort of get stuck in these, fluctuating states, or not fluctuating, rather oscillating states, sorry, when you're mostly reciprocal. When you have strong non-reciprocity, you enter a chaotic phase, which is known also from neural networks, for instance. And then when you get closer to zero sum, you go back to cycles that have slightly different properties. So I won't expand at all on this part of the phase diagram, but just to let you know. And so if you go back to the mostly reciprocal cases, you only find fixed points when actually the memory is good enough. So you need a nice amount of memory in order to find some of the exponentially numerous fixed points that I told you about, and so you can study how you get there in more specific details. But this is the important part first to remember, is that you need some memory. And so now the agents, they try implicitly to maximize their rewards. So what about these rewards and these fixed points? So here I've plotted the average reward in the system. And so when the memory is good enough, what I mentioned here, when the reciprocity is high, so just look at these points. And thanks to the work of Parisi and all the others, what we know is what is the global optimum. And it's this dashed line. So what you first observe is that actually the fixed points that the agents reach are significantly below the optimum. However, what's also important to note is that they're not so bad in the sense that they're about 8% below the optimum, whereas, a typical, if I randomly selected one of the exponentially numerous fixed points, it would be much worse. Okay, and so also thanks to the analytical work done in the past, you can compare the whole distribution of rewards among the agents relative to the global optimum. And what you find is obviously that many agents are worse off. And what's also interesting is that predicting which agents are worse off and which are better off, so where on the distribution they lie, you actually cannot do this. So it depends very strongly on the initial conditions. So here, I really want to stop on the fact that you reach fixed points that are not optimal, but that are still quite good, because without prescribing it in any way, what's nice is that we recover the idea of satisficing solutions that was introduced by Herbert Simon. So really, sort of spontaneously, without any behavioral rules, you recover this fact that probably finding something that's good enough sort of stops the system. And this is not what rational expectations predict, and it might be just something that arises mechanistically, let's say, from the complexity of the system. So now I need to go very quickly. But so just as a side note, a bit of noise, in fact, improves this a bit, even though the conclusion is the same. And just to close on something that I find personally very interesting is that if you do put a bit of fluctuations, the fact that you have these many fixed points in sort of a rugged landscape, if you imagine that there's energy associated to it, which is not always the case, but anyway, then you have something that's known in spin glasses as aging, which is that basically if you diffuse in this complicated landscape due to fluctuations, you get stuck in more and more deep minima in the free energy landscape normally. So here would be maxima, I guess, in the rewards. And essentially, the important part is that the decorrelation speed of the system depends on its age. And so I think this is quite important from the economic standpoint, because it means that here, without any external stimuli, you have a self-induced non-stationarity. And importantly, you can sort of decorrelate from where you are kind of suddenly, which would be, I guess, some form of crisis, just by waiting long enough. All right, so now I'll wrap up extremely quickly. So just to summarize in a nutshell what we worked on. So something that's known is that heterogeneities lead generically to complex solution landscapes that have many solutions. And this leads then to the non-stationarity aspect of thing as just mentioned. And these two things strongly break the usual economic assumptions. Then if you add non-reciprocity, really the only thing it does is further driving out of equilibrium, but it doesn't break that phenomenology as long as you keep it sort of, small. And finally, learning helps. However, it only leads to what we can identify as satisficing outcomes. And interestingly, it does so spontaneously, which suggests that it can be just a product, let's say, of the exploration of the complex systems and not of a behavioral rule. So in terms of future directions, I think, it'd be worth exploring maybe more realistic networks. Something I really like to do is actual experiments with people that I think is doable. And just to close, I think the idea of interplay between non-reciprocity and disorder is also an important notion in other complex systems, such as ecology and neural networks. So with this, I finish a bit late, but I invite you to please, take a look at the paper if you're interested, because there's many things I didn't have a chance to speak about. Thank you very much.
Thank you very much, Jerome. So, are there questions or comments? If not, I have one, but you have introduced two main ingredients, non-reciprocity and learning.
Mm-hmm.
For example, if you go back to the slide 10.
Yes.
Okay, the statement without learning never reach equilibrium. This statement is true even in the present and in the absence of non-reciprocity.
So, okay, it depends what you mean by equilibrium. So here, this is why I put it behind quotation marks, is that this is equilibrium in the sense of economics, so a fixed point. In terms of, actually statistical physics equilibrium, if you're in the case where it's fully reciprocal, then, okay, it's a bit of a peculiar case, because here, the cycles are sort of a byproduct of the fact that you do parallel updates. So if you introduce some finite temperature, then you reach equilibrium in the statistical physics sense, I believe.
Because there is no noise in this model.
So in the parameters I showed, there's no noise. You can, we did put noise, But so just for the sake of the argument, because I guess noise, so for us physicists, it's sort of the natural setting, but in the socioeconomic context, it amounts to being irrational, let's say, putting some uncertainty in the decision-making process, which is not the most obvious assumption usually. So I guess the zero temperature case is sort of the standard, and then you can introduce noise, which we did. But so here, what I'm showing is without noise.
But I mean, do your results are stable, let's say, with respect to the addition of a small quantity of noise, or perhaps they might change completely?
No, it's relatively robust. It's just that, of course, when you put noise, I mean, you need to sort of redefine what you mean by cycle, for example, because in our model, the thing is, when you put some noise, it's really at the level. So maybe, I don't know if this will help, but it's sort of at the level of the local field. So what I mean by this is that if you write the equations with noise, essentially the evolution of the local field will be noisy itself. So you don't have true fixed points. You sort of need to redefine quasi-fixed points, because if you have, essentially what I mean by this is that you always have fluctuations of order root alpha over beta. So either you take the memory to be infinitely long, and then you recover basically the picture of standard spin glass at finite temperature, or if it's not, you sort of need to account for these and take into account their existence. But overall, it's quite stable to the presence of noise. And we have another phase diagram with finite temperature.
Okay, thank you. So, no comments, no questions. If not, okay, let's thank again the speaker, Jerome.
Thank you.
Thank you very much.